Okay, so recording started. Definitely want to say good afternoon to everybody again. Okay, so but while we're getting started, just a few, just some announcements for today's class. So we're going to finish up confidence intervals today. Well, hopefully, I'm not exactly sure how far we'll get, but we'll get really close to finishing confidence intervals. And I'm going to do another example, just like we did, just like some confidence intervals like we did last class as kind of a refresher for to start today. Your homework number 6 is due next Tuesday. So it's posted in the classroom. So you go to the classroom under homeworks, homework number 6. So after class today, you'll definitely be able to do questions 1, 2, 3, questions 1, 2, and 3 for sure. And then we might start how to do questions 4 and 5, but we'll finish those up on Thursday, no matter what. All right. Just a reminder, last day of class is Thursday, the 6th of May. That's going to come like a lot quicker than we think. And so for today's class, what you're going to need a little bit later on, or initially to start, you're going to need your TI calculator. So have your TI calculator handy. Doesn't matter if it's a TI-83 or the TI-84. And then also under course content, under week 13, there's this thing called the T-table used to find critical values. If you click on that, all right, have this handy. You either have it, hopefully you printed it out. If not, just have it handy on your computer a little bit. But if you have a printer, it's worth just to print this out to have it handy while we go through our lecture. Otherwise, does anybody have any questions for me before I get started?
How was your weekend?
I'm sorry?
How was your weekend?
How was my weekend? That's you know what? I don't even remember my weekend. Isn't that weird? I know I did something. Did I do anything? I don't know. You know what? Every day feels the same to me.
If you didn't do anything, that's perfect. Relaxing day.
And I can tell you my weekend was not relaxing. Okay. I haven't been relaxed since like 2020. So like early 2020. Pre-pandemic. I haven't been relaxed. I haven't been relaxed since February 2020. Oh man, that's funny. Okay. I hope anybody else laugh at that.
Oh, I was laughing the whole time.
Okay. Oh man, I'm almost crying. Oh, tears of sadness, probably. Okay. Anyways, any other questions? Okay. So I want to start with this. This is kind of like a review example. Okay. So suppose that Apple Incorporated wished to estimate the mean talk time of its iPhone before the battery must be charged. Okay, so in a random sample of 30 iPhones, okay, so this is what you're given. You're given the sample size, n is equal to 30. You're given the sample mean is 350 minutes. And then next it says, assume the population standard deviation sigma is 90 minutes. So then you're given sigma 90. Okay, 90 minutes. Next it says, construct and interpret a 90% confidence interval for the mean talk time for all iPhones before the battery must be recharged. All right, so this is exactly from last class. Okay, confidence intervals are a range of values. Okay. So the formula for a confidence interval is always this. It's always the point estimate plus or minus what we call this margin of error. Okay, that's always the formula for confidence intervals. So next, point estimate, sorry. So the point estimate is X bar. The margin of error is made up of two things. The first is something called Z of alpha divided by 2. This is the critical value. Times sigma over the square root of n. And all this is the standard error. Okay, now you can absolutely do this by hand. Okay, so you can find a confidence interval by hand. You're more than welcome to do that on homeworks and on the exam. But what I like to focus on in this class, especially because we're remote, I want to make things more manageable for you all. What's the best way, do you think, to tackle these confidence intervals? It's using what? Using your trusty what can help us here. Calculator. Thanks, Alexander. Yeah. Falling back and let's have our calculator help us with this. Okay. So is everybody okay if I go to the next slide? So this is example 1 continued. Okay, so what we're going to do is we want to use our graphing calculator to find the confidence interval. So what you're going to do is the first thing you're going to press on your calculator is you're going to press the stat button. And then does anybody remember what I have to scroll over to next?
Test.
Yep. Awesome. Thank you. And then for this type of problem, what option did I say you would use? Thank you. Right there. Perfect. It's option number 7. It's Z interval. So we scrolled over. We went stat, tests, and then it was Z interval. So I'm going to scroll down to problem number or option number 7 here. And now if you have anything from the previous problem plugged in, you can just go right over it. So the standard deviation, just going back real quick, was 90. So I'm going to change that to 90. X bar was 350 minutes. And then the sample size is 30. Now remember your critical value, your C level here, this is your confidence level. Well, if you look here, I asked for a 90% confidence level. So I have to change this to 0.90. All right, so then I'm just going to scroll down and click calculate here. How many people got this right here with me? Awesome. Right? Your calculator makes this pretty straightforward. Yeah, I hope so. Yeah. So the confidence interval, what it gave me was, can you go back to what you put in? Of course. Stat, test number 7. It should look like this, Jamie.
I put that in, but I didn't get. I got 317.
317. Did you change the sea level to 0.90?
I think there's like a mark on my calculator, but I think it says. Oh yeah, it does.
So
It says 3. Yeah, I think I just put something in wrong.
yeah, that's all that happened. That's all you did.
Thank you.
Of course. So it was 322.97. All the way to 377.03. Okay, that's the construct part. Okay, next thing we have to do is interpret. Okay, we have to interpret this confidence interval. Okay, and look, what these confidence intervals do is they estimate the mean. They try to estimate the population mean. We go like this. We say, look, I know the sample mean was 350 minutes, but that was just from a sample of 30 iPhones. So from this sample that we collected, what's reasonable for the real population mean to be? And so it just goes like this. Based on this sample, we are 90% confident that the mean talk time, that's what we were estimating, the mean talk time for the iPhone is between 322.97 minutes and 377.03 minutes. All right. So what do you guys think? There's only so many examples I can do, but sorry, where you get the mean talk time again? I don't understand what you mean by that. Like this part right here from the original problem, is that what you're asking? Yeah, it'll be given in the problem. Or as you'll see later on when we do a different type of example, I'll either tell you what the sample mean is, or I'll just give you the original data set. So I'll have an example that requires an extra step in a little bit. Okay, so is at least using the calculator pretty straightforward? Okay. All right, so if you look back at your calculator real quick, when you hit the stat button and you scroll over to tests, you see option number 7 where it says Z interval. Does everyone see option number 8 where the next thing it says is T interval? Can you guys let me know in the chat if you see that option number 8, T interval? Okay, awesome, thank you. Like, what the heck is this, right? I see this Z interval, okay, but what is this T interval? So that brings us next to constructing confidence intervals using something called the T distribution. All right. And let me kind of just set up what this is and why we need it. And I'm going to do the next maybe 20 minutes of class is going to be like a little bit of theory type stuff. And then we're just going to jump right into examples. So if stuff doesn't seem to like make too much sense initially, just remember, like, as soon as we do the first example, it's like, oh yeah, I got it, man. I got it. Okay. So this next part here, this T distribution, this is like basically how we do confidence intervals in the real world. Okay. So actually, all the examples that I've done previously isn't exactly how confidence intervals are constructed for means in the real world. So the reason being is in the previous examples, you were given sigma, okay? All right, what I mean by that is you were told something like this. Assume the population standard deviation is, and then I would give you some number. Like, I'm going to quickly go back and show you what I mean by that. So like in this example, assume the population standard deviation is 90 minutes, okay? So like in the real world, you probably will not know what the population standard deviation is. Okay, you won't know what it is. Okay, but here's the thing. It is an incredibly important number. Like we need it for our formulas for this stuff. Sorry, daycare just sent me a picture of my son, so I had to like just take a quick look. Looks like he's having a good time. I just wanted to update you all on that. I don't know why. Okay. Thanks. A few people were like, "Oh, cute. Thanks for sharing." And I can see the collective eye roll of everybody else in the class. So, thank you for bearing with me, though. Okay. So go back to this, we need the standard deviation in our formula to construct confidence intervals. I'm going to put CI for confidence interval. Like if you look, this was the formula that we had. It was X bar, add and subtract, Z of alpha divided by 2 times sigma over the square root of n, okay? Like sigma, the standard deviation, part of the formula. Okay, part of the formula. So if you don't know what it is, okay, like if you collect a random set of data, like you don't know what the population standard deviation is for what you have under investigation here, okay? So we need to solve this problem. And so what happens is okay, since we don't know sigma, all we do is we estimate it with the value S. And what S is S is the sample standard deviation. Okay. But what's really interesting, okay, what's really, really interesting is when you do that, okay, so when you replace sigma with S in your formula, so X bar, add and subtract. I'm going to leave this blank for a second, times S over the square root of n, okay? It turns out that you can no longer use a Z critical value. Okay. What ends up happening is your standard error here, all right, your sigma divided by the square root of n, it's no longer related to a normal curve, okay? your standard error no longer can be related to a normal curve. To normal distribution. Okay. And what ends up happening, or what was discovered, is this new distribution. Okay. It ends up being what's called a t distribution. And I actually like to give just a little bit of backstory about the t distribution. Because I actually think it's a really interesting story. So when you study mathematics, right, when like you study algebra and geometry, like that's thousands of years old. When you study calculus, like calculus is what, 600 years old. But statistics is kind of like a new branch of mathematics. So this t distribution was discovered by a company that's still around today. Just out of curiosity, has anybody ever heard of the company called the Guinness Brewing Factory? Have you guys heard of this company? I mean, come on, has that people heard of Guinness beer? It's kind of a joke. People, decent beer. Okay, all right. So this is really interesting. So there was this gentleman who worked at Guinness Brewing Factory at the end of the 1800s and early 1900s, named Gassot. And what he actually was, believe it or not, was he was actually a brewmaster for Guinness. So what Guinness did was, this is why this is such an amazing story. Guinness employed mathematicians, okay, to help them make better beer, which I think is like really cool story. Anyway, so he was studying this type of problem where he said, I don't know sigma, so I'm going to use this S, but like, oh my gosh, it's no longer normally distributed. I've discovered this new distribution called a t distribution. And he wanted to publish his results because he's like, this is groundbreaking in the field of statistics. And Guinness Brewing Company went to him and said, no, you cannot publish your results. You work for us. You have to keep it in-house. And he was like, no, I'm going to do it anyways. So he published it anonymously as the name student. So sometimes the t distribution is called the student's t distribution for that reason. And it's actually like really cool. I'm just curious, has anybody in the chat ever been to Ireland? Matthew has? That's cool. Did you go to the Guinness factory, Matt?
No, I didn't, unfortunately.
Oh, that's the best part of Dublin.
I actually didn't go to Dublin. I actually went to Cork and then southern down south towards Shull. So
I've been to Cork. Barry, have you been to? Did you go to the Guinness Brewing Factory?
No, I didn't go either, unfortunately.
What? Oh my god. It's like the best part. Anyways, I'm like shocked. All right, you guys need to book trips when you can travel again and go back and check that off your list. But if you find yourself in Dublin, okay, and you're of drinking age, okay, you should definitely go to the Guinness Brewing Factory, because when you take the tour of the Guinness Brewing Factory, along the path, there's this little plaque literally for Gassot, and it says discovered the students' tea distribution. So I went to Ireland with a buddy, like, oh my gosh, like 10 years ago. And I made him take a little picture of me at the plaque. And then when you get to the top of the Guinness Brewing Factory, they give you a free Guinness. It's not really a free Guinness because you have to pay to go on the tour, but it's part of the tour. So when you have your first Guinness, you should cheers to Gassot. Okay. So I hope you guys found that a little interesting. Or not, I can't tell. But so what I want to do now is I want to kind of explain to you what the t distribution is. So is everybody okay if I go to the next slide? Okay. So what is a t distribution? So if you go back into the classroom, and remember, go under course content, and go to week 13, click on this t-table thing, okay? And you should see this table right here, okay? How many people have this with me, maybe on your computer or printed out? Okay, I got one, I got a couple of yeses, okay. All right, so look at this distribution right here. Okay, what does this look like to you? What does it almost look like? Does it look like, starts with an N? Does it look kind of just like a normal curve?
Yes.
Yeah, it totally looks like a normal curve, almost, right? Like Matt, this looks just like the normal curves you were drawing, and to a certain degree, yes, but there's actually some subtle differences. So it looks like a normal curve, but with some differences. Okay. So let me give you the properties of the t distribution. And it turns out it has many of the same properties as the normal curve, okay? The first one is the area under the curve is equal to 1. Okay, so just like with the standard normal curve, okay? So what this means is the t distribution is also a probability distribution. Okay. But the good news is, I got some really good news, is we're not really going to use it too much to compute probabilities in the traditional sense that you're used to. So we're not going to look to the curve to calculate some probability. So that's good. Okay. Just like the standard normal curve, the t distribution is centered at 0. If I could spell. All right. This is also just like the standard normal distribution. The third property is the curve is symmetric. All right. What is, help me out again. Can anyone tell me what it means when I say a curve is symmetric? What do you mean by even? I think you know what you mean, but like, what do you mean by that? Yeah, like what it means is like if yep, kind of the two curve even and same on both sides. Like if you were to cut the curve in half and fold them over on top of each other, it would be the same on both sides. Okay. So this is also just like a normal distribution. Okay. The curve, you can fold it onto each side. There's 3 more properties I want to get through. So let me know when I can go to the next slide. Everybody okay if I hop to the next slide?
Yep.
Okay. Okay, so what we had said here is it looks like a normal curve, but with some differences. So the fourth property is the t distribution. Looks like a normal distribution. But the big key difference here is it's just with more area in the tail. More area in its tails. So you're going to hear me say this kind of about the t distribution. It's going to be shorter and wider. Okay. And I'm going to do some visuals so you can see that, okay? The fifth property is the t distribution looks different. I'm just going to say looks slightly different based on the sample size. Based on the sample size you have. Okay, so our sample size is n. And then the sixth property is as the sample size increases, okay, so kind of going back to just like the basic concepts of statistics, is as you collect, and there's more to that sentence, but as you collect more data, is more data better than less data? Is it better to, yeah, totally. Like you want, the more data you have, the better. Okay. So as the sample size increases, the t distribution looks more normal. Okay. And what I say by looks more normal, it becomes more normally distributed. All right. It gets closer and closer and better of looking to more like a normal distribution. Okay, so here's the big takeaways of the t distribution. Okay, it looks kind of like a normal curve. Okay, it has same basic properties. All right, but it's a little bit shorter and wider, and I'll do a visual to show that. The t distribution is going to look different based on your sample size. And then again, as the sample size increases, what happens is this thing called this t distribution, okay, this t distribution becomes more normally distributed. All right. Is everybody okay if I go to the next slide? Yes, sir. Okay, thank you. Oh, yep, I'm not in any hurry today. Okay. All right, so let me show you the visual of this, okay? Okay, so a visual of the t distribution, okay? All right, so I'm going to draw a number line, and here's 0, Okay. So the first thing I'm going to do is I'm going to actually, even though I'm saying a visual of a t-distribution, is let me draw a normal distribution first. Okay. So suppose this is right here. A normal distribution. Okay. All right, how did I do on my drawing? Not too bad, actually. What do you guys think? Pretty good, normal distribution?
Casso.
Wow, I can't believe I only got one accolade there. Yeah, this looks phenomenal. I don't know what you guys are all thinking about here, but so what I want to do is this is the thing. Okay, the t-distribution looks slightly different based on the sample size, and as the sample size increases, you become more normal. So the first thing I'm going to draw is a t-distribution of sample size 10. Okay. So this dotted line here represents a t-distribution with sample size 10. Do you guys see how it looks like a normal distribution, but it's like, it looks like I pushed it down, I flattened it, I like pushed it down, and then as I pushed it down, the tails got more area under them. Do you guys notice that? Like it's not as tall and it has more area in the tails. Okay. That's what I mean by it looks going back shorter and wider. Okay. It's shorter. The top of the curve is shorter and there's more area in the tails. Next, I'm going to draw a t-distribution with sample size 30. Okay. Do you notice as I increase the sample size, the curve got more and more normal looking, like it's like it lost some area in the tail and it got taller, but it's not exactly perfect. That's the whole difference here. Okay. The t-distribution is just going to look like a normal distribution. Okay. It's just going to be shorter and more area in the tails. Those are the big differences. Okay. Is everybody okay if I can go to the next slide? Okay. I got one yes, so I'll move on. Let me know if I need to go back, okay? So the next question is like, when will we use this t-distribution? Okay, so it turns out the t-distribution will be used in two places, okay? One for confidence intervals. Okay, which is what I'm going to show you next. And we'll actually get to it after the break. And then the next thing we're going to use this t-distribution for is in hypothesis testing. Okay, and this is going to be on Thursday and next week. Okay. And this hypothesis testing is our last topic. Woo! And this is and you know what? I understand all this stuff is confusing, but like a lot of it is like, okay, when how am I going to know I'm going to need to use this thing you've been talking about for 20 minutes, Matt? And so the way you'll know. So how you'll know to use t-distribution. It's whenever you're given S, okay, you're given the sample standard deviation. Instead of sigma, okay, which is the population standard deviation. Okay, so whenever a problem gives you S, the sample standard deviation instead of the population standard deviation, it's like, okay, I'm going to need to use this t distribution. Okay, that's going to be the giveaway for this. All right, and so instead of like doing one example and taking our break, why don't we take our break a little early today and then come back and we'll just do all the examples during the second half of class, so that there's no breaking up of topics. Okay. Does that work for everybody? I like that response. Sure. Whatever you want, Matt. You're in charge here. And then I'm always like, am I really though? I don't know. Okay, so it is now 1:44. So can I go to the next slide real quick? So let's take our break. Let's do 1:44 p.m. Let's go to 1:55 p.m. Okay. It's basically 1:45 now anyways, okay? So I'll see you in 10 minutes. All right, everybody. You guys hear me okay again?
Yes, we can.
All right. Let's finish up. All right, let's finish up for the afternoon. All right, finish up because it's so nice outside. I want to go for another walk. So, anybody been outside yet today? Nobody? Well, hopefully after class today. Yeah, it's nice out. Hopefully after class, if you haven't been outside, you should go for a 20-minute walk or something. It's just so nice out. Okay. All right, so going back, this is kind of just, instead of showing you how to read this t-distribution table and then doing examples, I'm gonna have us do examples, and then in the middle of the examples, learn how to read the t-table. So have your calculator handy because we're gonna use that as well. And then also have this t-table printed, okay, and ready to go. All right, so in general, why do we need confidence intervals? So this is an old slide that I always used to do this example about the SARS virus from a long time ago, but I guess COVID is actually a version of a SARS virus, so it kind of relates. But before COVID-19, does anybody remember? This was maybe like 10 years ago, so I don't know if people remember. But does anybody remember when the first like SARS outbreak happened? And we thought it was going to be a big deal, and it ended up not being that big of a deal. Do people remember that? I'm curious. Nobody? Yeah. You got one person, me? No. Okay. It's okay if you don't. So like 10 years ago, we had our first like brush with the SARS virus. Okay. You read about it before. Yep. And luckily it didn't turn into a big thing like COVID-19 did. But so just imagine, or just kind of think that there's this new virus that comes out, okay? This new SARS virus that comes out. And suppose what you want to do is you want to estimate the mean incubation period, okay? Does anybody know what an incubation period is for a virus? Anybody in the health sciences here who might know? Not necessarily. You're close. Okay, it's how long it takes. You're close, Jamie. Before you show symptoms. All right. So like imagine I come in contact with like even COVID-19. Like imagine I come in contact with this virus and it enters my body. Do I generally become immediately sick? Like as soon as the virus touches my body, do people generally get sick, or does it take a few days till it starts like getting into your body? It takes time. And that's what an incubation period is like how long it takes before, oh man, I think I'm sick. Okay. So now everybody has a different incubation period, right? Because everybody has different immune systems. Okay. So imagine you get a job out of school working for the CDC. Do you think it's important to know the average incubation period for a new virus? Like if you want to fight a virus, do you think it's important to know like on average how long it takes people before they start showing symptoms? Like, yeah, it's like very important. It is incredibly important. Okay. So how would you do it? Like how would you estimate the mean incubation period? You just would take a sample, obviously. Okay. So this is actually, we're going to do, this is not made up data. Okay. This is pulled from a CDC report. Okay. So we're actually going to calculate a confidence interval that was listed in a CDC report. Okay. So a lot of times, I'll be honest with you, a lot of times I come to class, I make up this data. This stuff is not made up. All right. So in a sample of 81 SARS patients, okay, so that's our sample size. it was found that the mean incubation period of those SARS patient was 3.8 days. So this is the sample mean. And on top of that, what also happened is the standard deviation, okay, for incubation period was 15.1 days. And this is the sample standard deviation. And this is important. Note that you're given S, not sigma. Like, and there's the reason you're given S is because like it's a new virus. There's legit no way you could know what the real population standard deviation is, okay? So let me ask you this next question here. And let me know if everyone's okay if I go to when I can go to the next slide. Do you think, yep, nope, take it. I have a tendency to go fast. I'm sorry. So my question, here's kind of like a question for you. Is the population mean incubation period of everybody who could come in contact with SARS exactly 3.8 days? Like, do you think, so we talked to these 81 patients, right? And the sample mean of these 81 patients was 3.8 days. Like, do you think that the real mean incubation period of everybody is exactly 3.8 days? Yeah, exactly. No, it's not. It might be close to 3.8 days, but it's not exactly 3.8 days because this was just a sample of 81 people. Okay. So then so the answer is no. Well, then what could the real value be? Or what could the exact value be? Again, there's no way to know, so we can't know this. So what we do is we estimate with a confidence interval. Okay. So is it okay for me to go to the next slide? Okay. All right, so these confidence intervals, okay, this is constructing a confidence interval for mu, okay, so for a population mean. When sigma is unknown. Okay, so this is when you're using S, the sample standard deviation. So confidence interval is a range of values, which is the lower bound and the upper bound. So it's the point estimate plus or minus your margin of error. Okay. So this is your sample mean plus or minus your critical value times your margin of error. And this is the biggest difference. Okay, your critical value is no longer a Z critical value. Okay, it's no longer a Z critical value. So our new formula, whenever you use S, looks like this, okay? So this is our new formula. Okay, notice sigma is replaced with S. And that Z of alpha divided by 2 is replaced with this new thing called T of alpha divided by 2. Okay. So this X bar we know is the sample mean. Let me go back just so you can see this. X bar is the sample mean. N is the sample size. And S is the sample standard deviation. So the new thing that we've never seen before is this T of alpha divided by 2. Okay. And this is what this T of alpha divided by 2 is what is called the T critical value. So if you look here on this table, okay, does everybody see on the table here, literally where it says T distribution critical values? Do people see that on their table?
Yes.
Okay. So all this table gives, all this table does is this table no longer gives probability, okay? All it gives is these critical values, okay? That's all the table does is it gives critical values, done and done, critical values, done. So if you look at the table here, just like with the normal table, you're going to need to know two things. You're going to need to know this thing called upper tail probability, and then you're going to need this other thing called DF, okay? And once you have those two things, like a DF of 14 and an upper tail probability of 0.05, you just kind of like look where they intersect, and that would be your critical value right there. And we're going to practice this. So the DF stands for degrees of freedom, okay? And the degrees of freedom are the sample size n minus 1. So where does this n minus 1 come from? If you recall, the formula for S is the square root of the summation of each x value minus x bar squared divided by n minus 1. This was the formula. So it comes from the standard deviation formula. In the upper tail probability is alpha divided by 2. Now, does anybody remember what alpha is called? Our level of significance. But do you guys remember I also called it my willingness to be wrong? Do you guys remember me saying that a while ago?
Briefly, yes.
Yeah. So like, you know, if you want to construct a 95% confidence interval, okay. You're going to be wrong 5% of the time. So alpha was 0.05. All right. So you need to know your degrees of freedom, okay, which is the sample size minus 1. And then you need to know your alpha, which I'm going to give you, and you divide that by 2, and that's going to be what's called the upper tail probability. So you can see here, DF, degrees of freedom, whoop, right here, and then upper tail probability right here. Okay. So a lot to go here, a lot to look at here, but I promise you it's actually not that bad. All right, is everybody okay if I go to the next slide?
1 second.
Yep, no problem, no problem.
All right, I'm ready.
Okay. Can you guys hear my chair squeaking? Really sorry about that. If you guys can hear it, I'm sorry. When I got this chair, it was brand spanking new and it never squeaks. And now I'm also just like a fidgety person. So whenever I move a lot. So I'm sorry about that. Okay, so here's the example, going back to this, okay? So in a sample of 81 SARS patients, it was found that the mean incubation period was 3.8 days with a standard deviation of 15.1 days, okay? So this information was all given to you. Okay, so let's construct and interpret a 95% confidence interval. Okay, so when you're 95% confident, that means your alpha as a decimal is 0.05 because you're going to be wrong 5% of the time. So let's construct and interpret a 95% confidence interval for the mean incubation period of SARS. So this is the confidence interval for the average incubation period. Okay, so here's the solution. So this one, I'm just going to do in the slides, and then for all the remaining examples, we're actually going to do it by hand. So I just wanted to put this one in the slides so we can concentrate on. Okay. So to construct a confidence interval in this class, we're going to use this formula. Okay. And you use this again when you're given S instead of sigma. Okay. So look, X bar was given, okay? X bar was 3.8 days. S was given, okay? The standard deviation was given. It was 15.1 days. And N is given, that was 81. So what you need to find is this T of alpha divided by 2. Okay, so let's grab our table because we're going to look it up on our table here. Okay, the first thing you're going to need is this thing called DF, degrees of freedom. Well, does anybody remember what I said the formula was for DF, degrees of freedom? All right, it's n minus 1. So that's 81 minus 1 is 80. So look on the chart. As you go down DF, do you see the number 80 here? Do people see that? Anybody else see that? I see Bertha sees it. Or nope, yep, okay. So there's 80, that's your DF, okay? So the reason, so the T distribution always uses degrees of freedom called, or equal to n minus 1. And the reason is, if you look back here, so our formula uses S instead of sigma, okay? Like right here, we're using S instead of sigma. If you go back to like our third lecture of the class or something, the formula for S, the sample standard deviation, was this formula right here. And the denominator of that formula was n minus 1. That's what was called degrees of freedom. And that's where that n minus 1 comes. It's like, okay, so since we're using S, the sample standard deviation, and it has what we call degrees of freedom n minus 1, that's where we're going to look up on the corresponding table here. That's where this whole n minus 1 comes from, Jamie. Okay. The next thing you needed on this table was this thing called upper tail probability. So I'm just going to call it UTP. And that's alpha divided by 2. So I wanted a 95% confidence interval. So I'm going to take 0.05 and divide it by 2 to get 0.025. Well, look on your table here. Do you see, does everybody see 0.025?
Yeah.
Yeah. So now let's check it out. Let's see where 0.025 intersects with 80. If you look up here, it goes 0.025. I made it too big. And you scroll down to 80. Do you guys see the value 1.990? Yep, I got it right there in the chat too. That's our critical value right there. Was that table pretty easy to use? Or not too bad, at least, once you know the formulas of D? Yeah, it's not too bad. So then all you literally have to do then is just replace it in your formula now. So it was 3.8 plus or minus 1.990 times 15.1 over the square root of 81. And just to shave a little time so we can get to the next examples, but if you if you plug this into your calculator, you'll get roughly 3.3. And then so the lower bound here for the confidence interval is the subtraction part. So if you take 3.8 plus or minus 3.3 or minus 3.3, you get 0.5. And the upper bound 3.8 plus 3.3, you get 7.1. Okay. So what this means is look, I have no idea. I have no idea what the real mean incubation period is of this SARS virus. Okay. So look, I did talk to 81 people. And based on this sample of 81 people, I'm 95% confident that the mean incubation period of SARS, and this is crazy, and this is true, it could be as low as half a day. Okay. It could be. And then it could be as high as 7.1 days, which is crazy when you think about it, like how big that interval is. But that's generally when you see reports like this, what you'll see next to it, and this is if you ever go to graduate school or when you get to taking big upper division courses, reports will say stuff like this. It'll say mean, and then you'll see something called 95% confidence interval. And it would say something like, look, the sample mean was 3.8, but our 95% confidence interval is this. So these big statistical reports like this will always include a sample mean and then a 95% confidence interval, because we know that the real mean is not exactly 3.8 days. So what could it really be? Okay. And that'll help us, help like people who try to fight these viruses, right? They'll be like, okay, well, you know what, on average, it could take people a week to start showing symptoms. Okay. So that's why, that really is really beneficial to know. All right. But, for now, was using the table not too bad? Not the worst. We're gonna do another example to practice it. Crickets, huh?
It's
Nothing.
not too bad.
Not too bad.
Yeah.
Everybody ready for the end of the semester is kind of the sense I'm getting. Okay. Yes, me too. Me too. All right. So I also in the slides here, I wrote it on it, but I also showed you how I got it here in the slides. All right, let's see, I got 3 more examples we'll do for the rest of class. So by the end of class, you'll be a master of this, I promise you, okay? All right, so here's the next problem, okay? And we're gonna do this one by hand, and then I'm gonna show you the calculator, okay? So suppose an economist wishes to estimate the mean commute time of workers in Westchester County. Okay, he or she, this economist, she wants to know, I don't know, on average, how long does it take people to get to work? So that's we'll just use she. She wants to estimate the mean commute time. Okay. So the economist, she obtains a random sample of 31 commuters in Westchester County. Okay, so let's just start with what you're given. You're given n is equal to 31. Okay. And finds the sample mean, which is x bar, to be 31.2 minutes. Okay. And the sample standard deviation. So the sample standard deviation. So that's S to be 12.1 minutes. Okay. Let's construct and interpret a 90% confidence interval for the mean commute time in Westchester County. Okay. So when you get these problems, okay, these confidence interval problems, look at the standard deviation, okay? Based on what I've been talking about, is this a Z or a T critical value problem? And how can you tell? Okay, so notice. Perfect. You guys got it both there. You're given S. Okay, so you're given the sample standard deviation. So what that means is you're going to need to use the t distribution. Okay. So the formula you're going to use, it's X bar, add and subtract this t of alpha divided by 2 times S over the square root of n. Okay. Well, look, you're given X bar, you're given S, you're given n. The only thing you need to find is this t of alpha divided by 2. So the first thing you're going to need to be able to use this table here is you need this df, degrees of freedom. Okay, df. Well, that's n minus 1, the sample size minus 1. So look, that is 31 minus 1, and it gets you 30. All right, so go to your table. Can you find 30 on your table here? Does everybody see 30 on the table? Yes. Awesome. The next thing you need is this thing called upper tail probability, but I'm also going to show you another cheat sheet way to do this, okay? If you scroll down to the bottom, does everybody see this thing called confidence level? How many people see confidence level at the bottom? I muted somebody. I think somebody had some music on in the background. But if you don't like this upper tail probability, okay, there's this thing down at the bottom called confidence level. Well, if you look, I set a 90% confidence interval. So you can go, well, look, here's 90. And I'm going to scroll up now to 30. And what critical value do you all see? Do people see the number 1.69? Yep, Jamie's got it. Does everybody else see that? And you would get the same thing if you did the upper tail probability. You could say, well, 90% confidence interval, that's 0.10 divided by 2 is 0.05. 0.05. I actually find just using the confidence level at the bottom is a little bit easier. So that means my critical value is 1.697. And so after you find that, you just plug it into the formula. So this is 31.2, add and subtract 1.697 times 12.1 over the square root of 31. Yes, you always divide by 2 if you're going to do it by hand. All right, so let's grab our trusty calculators. And what we got to do is we have to figure out this margin of error first. Okay. Come on, calculator. Why are you giving me a hard time? So it's 1.697 times 12.1 divided by the square root of 31. How many people got this number right here? 3 point, I'm going to round it to 2 decimal places. 3.69. Okay. So that's my margin of error, 3.69 here when I round it. All right, so that means the lower bound of the confidence interval is 31.2 minus 3.69. And you should get 27.51. And the upper bound is 31.2 plus 3.69. And you should get 34.89. So look, the way you would interpret this is you just say this, look, based on this sample, we are 90% confident the mean commute time in Westchester County is between, look, the average could be as low as 27.51 minutes. And it could be anywhere in between and up to, it could be as high as 34.89 minutes. And that's it. Okay, so really like the hard part here was figuring out what the critical value is, you know, and then once you figure out what the critical value is, you know, then it just becomes kind of like a plug and chug problem. All right, what do you think? Not too bad doing it by hand, or you ready for me to make it even easier for you? All right, well, let's grab our calculator now, okay? And look, let's see if we could do this by hand or with our calculator and see what the calculator gives us, okay? So everybody hit the stat button on your calculator. Grab your trusty calculator. And let's scroll over to tests. And look at this. I know that I'm going to need to use the t-distribution. So let's scroll down to number 8, okay? Whenever you want to use this, the calculator to compute this formula for you right here, it's option number 8. So go to the t interval right here. And you should see something like this. Up at the top, it says two things. It says data or stats. Like scroll over to stats here if it's not already highlighted, okay? Because what this means is you're given the summary statistics, stats. So your X bar here, okay? That's the 31.2. So everybody type in 31.2 here. S sub X, that's the standard deviation. So look, that was 12.1. N was my sample size. Well, that's 31. And then your C level, I want it to be 90% confident. So that's 0.9. So if it says 0.95, just make sure you change it to 0.90. And then everybody go to calculate on your calculator and hit enter. All right. How many people on their screen see what I have there?
Yes.
Yeah. Check this out. Look. When we did it by hand, we rounded to 2 decimal places, got 27.51, 27.51. When we rounded to 2 decimal places, we got 34.89. Look, when we rounded to 2 decimal places, we got 34.89. Not too, so as soon as you go to the calculator, boom, right? Damn, much easier. Yeah. I think everybody's just like, Matt, like, what the heck? Why don't you just show us that to begin with, right? Yeah, yeah. So I went stat. I went over to tests. And it's option number 8. Okay. And then you want to click on stats. Okay. And then you're just going to input those values that I have on the screen there. All right. So what I want to do next is I want to do, did that help clear it up, seeing it go through one more time?
I did.
All right. So notice how there's 2 options here, data and stats. I want to show you an example with data. And this will probably be our last problem for class. And then when we come back on Thursday, we'll do one more of these as a review. Okay. So if you guys remember, I introduced this section talking about this gentleman named Gassot. So I actually want us to do on this next slide, the problem that he introduced, or the problem he did in his paper, that introduced the t-distribution, okay? So here's the problem. In 1908, W.S. Gassot published the article, The Probable Error of a Mean, okay? So in this pioneering paper written under the pseudonym student, okay, that's where the student t-distribution come from. As I said, he published it anonymously. Gassot introduced what later became known as the student's t-distribution. So Gassot used the following data set. Okay, so we have this additional data set, which gives the additional sleep in hours obtained by a sample of 10 patients. I'm not even going to try to use this word. Okay, whatever. This something L-hydrobromide. Okay, I'm just going to call it the sleep drug. Okay. So this drug is probably not an approved drug to nowadays, okay? Probably like at the time in 1908, this drug was like, I don't know, probably did something to knock people out, okay? And what this data set, this raw data gives is the additional sleep in hours for people who take the drug. Okay, so it looks like somebody got like anywhere from 1.9 additional hours, 0.8 additional hours, 1.1, 0, only got one, additional 0.1 hours. This person actually lost sleep. This person got 4.4 additional hours, that's awesome, 5.5 hours, and so on, okay? So notice here, I don't even give you the sample mean or standard deviation. I don't give you anything. I just give you the sample size, okay? But I give you the raw data. So the problem says, determine a 95% confidence interval for the additional sleep that would be obtained on average for all people who use this sleep drug. Okay, so when you're given the raw data, just plug it into calculator. So everybody grab their trusty calculator, okay? And what we're gonna do here is we're gonna go back and we're gonna submit this data into the calculator. So we gotta remember how to do that. So everybody hit the stat button on your calculator, okay, stat. So we're not doing any calculations, we're not doing any tests. So I just got a direct message. It's no problem. Don't even sweat about it. When I got my second vaccine shot, I was destroyed for an entire day. Okay. Don't even worry about it. All right. So edit under number 1 here. You want to edit the list. So everybody hit enter. And in your calculator, if you have any data already in your calculator from a previous example or something, remember you go to the top and it says L1 and you hit clear and then enter. Okay. This is incredibly important. Yeah, no problem. Does anybody's calculator not say L1 here? Needs to say L1. Okay. So then what we're going to do is we're going to start inputting this data. Okay. So let's do this. 1.9, 0.8, 1.1, 0.1, minus 0.1. Someone got an additional 4.4 hours, additional 5.5 hours. That must be nice. 1.6, 4.6, and then 3.4. Okay. So I've got this data. Data is literally plugged into my calculator. Okay. So now I want the calculator to construct this 95% confidence interval for me. Okay. So everybody, let's hit the stat button on your calculator next. After you have it plugged in, everybody hit the stat button. And I'm going to scroll over to tests now. Okay. Now, was I told what the population standard deviation was, or was I just given raw data? Like, did the problem in anywhere say, assume the population standard deviation is blah, blah, blah? It didn't say that, right? Like, no. So then you're going to scroll down to number 8. You're going to want this T interval. Okay. So when you have the T interval, just hit enter. And do you notice over here where it says data? Everybody scroll over to data and hit enter. Okay. Notice now your calculator is going to be like, okay, yeah, whatever, man. Like, where's your data? Well, that's why where it says L1. So that's why you wanted L1. And then scroll down to confidence level, C level. Just make sure you change that. It says to 95%. So 0.95. Okay. And then next, hit calculate. Notice what it did for you is it figured out what X bar was for you. It figured out what the sample standard deviation was for you. And then it just ran through the calculations for you. Lickety split like that. Okay. How many people have these exact values on their calculator in front of them? I got one, I do. I got another, I do. Those were the best words I ever heard from my wife. Oh. If you have a sample size of 9, it means you missed a number. You just got to go back and make sure that these were, you plugged all these values in. Yeah, just go back and just, find the missing one and plug it in. Okay. But right now, boom, that's our confidence interval right there. Okay. So it's 0.8898. I'll go out 3 decimal places. 0.898. And then the top part was 3.762. Okay. So look, this is what we're saying, based on this sample. We are 95% confident that the mean additional sleep when using this sleep drug is between 0.898 hours and 3.762 hours. So when you're given the raw data, is it like pretty straightforward to use the calculator? You know, it's like that, just that extra step, right? You just got to plug the data in, but then is it not too bad? All right, good. Anybody else, like it wasn't too bad, or was it bad? I maybe give me it was okay. Or not. Okay, not bad. Well, thank you for the one not bad. All right, let me leave you with this question then. Would you all say, was this drug effective in increasing sleep? Like, could they advertise this drug as being effective at increasing sleep for people? And why could they do that? If they could. All right, well, let me ask you all this, okay? Yeah, I agree. Yeah, they could. Yeah, for sure. For sure they could. Is our confidence interval, you know, is the lowest value of our confidence interval still greater than 0? Like, what we're saying is, like, look at our confidence interval. Yes, we're like 95% sure that the mean is some number above 0, that it's basically between 0.9 and 3.7 hours. And it's like, yes. And this is because our confidence interval is above 0. Okay, like if this was, if the confidence interval went from a negative number to a positive number, then we could not say, you know, it was effective. But because our confidence interval is wholly above 0, like, yeah, this drug, this sleep drug was definitely effective at increasing sleep. All right, everybody. So what I want to do, I'm going to save this example for the first example we do next class on Thursday as kind of like a refresher example. And I'm going to stop the recording now.